Welcome back, folks. What we're going to do today, we're going to have a little bit of fun with a little 8-bit computer system, and we're going to look at pulse width modulation. We're going to discuss what it is, and we're going to show you what it's used for. And we're going to do all this on this little 8-bit computer, and eventually we're going to hook it up to this fan here through this optically isolated MOSFET module, and we're going to control the speed of this fan. So let me kind of show you how this thing works. This is just a little 8-bit computer based on a 6502. It's a design I put together maybe about 8 or 9 years ago. This particular model of it runs at 14 megahertz, so it's not too bad. It's got 32 kilobytes of memory, 32 kilobytes of ROM, a little bit of space in there for I/O. And then the I/O comes out and goes through this set here of bus drivers and drives this little 3-slot bus. Now this is one of the cards I made up for it. It's a pulse width modulation output, and it's got 2 ports on it, an input port, an 8-bit input port, an 8-bit output port. And it's also got like a bus access, but we're only interested here in the pulse width modulation. And that we'll just put that in slot 0 there, or slot 1. And let's hook up a scope to this. Okay, we should have the scope on up here and the terminal open to this little computer up here. And so let's reset the computer. All right, we want to cold start. Here we go. We have the pulse width modulation controller at location 33024. So let's set that to 50% modulation. All right, you see that on the scope. Now the way this is connected up right now, it's inverted. So low is high, low is 1 and high is 0. So when I say 100% pulse width modulation, that's when the trace is low, and 0% pulse width modulation is when the trace is high. And so let's bring in a little program which I have prepared here. Okay, so this little program here, what it does is, first of all, we set a variable f to 10. You'll see what that means. Then we do a loop from 128 to 0, step 1. So that x is going to be the actual pulse duration. And then we put in here t equals 0 to f. So it's kind of a little timing loop here to adjust the speed of the modulation itself. And then we update the pulse width modulation controller and repeat, and then we do it again. We count that from 0 to 128 and do the same thing again, except for just the opposite direction. So let's see what that looks like when we run it, when we execute it. Okay, there we are. We're going a little bit faster than the scope can keep up, or not the scope, but OBS anyway. So why don't let me change that. So we have 5, f equals, let's try 25 here. Okay, I think OBS is keeping up a little bit better this time. And that's one of the things I like about using systems like this for this sort of development. I could use a microcontroller, I guess, but having to reprogram the microcontroller every time and then pull it out and put it into my breadboard or whatever it is I'm doing, it's just it's laborious. But I can configure this little system whatever way I want, and I can update the program on the fly. So it becomes very handy that way to work with this. So there we are. We're modulating the pulse width. Let's slow it down a little bit, and then we're going to hook up this fan to it, and we'll see one application of pulse width modulation, that is controlling motor speed. Let's Control C out of that. We'll change F equals, let's try 200 for the motor. And let me hook up the motor to it, and we'll come right back and we'll run that program. Okay, here we are. We've got this set up now to control this. I'm going to turn the power on to the motor. We have my little puppy dog in the background making lots of noise. And we have the pulse modulation set to 0. It's high, so there's 0 modulation there. And now let's run that program. Let's see, let's make sure it's still there. It is. And we'll run that and see what that does to the motor. Here we go. Yeah, we could always change that line 5 there. Let's try 50. See if the motor can keep up with that. It probably won't keep up with it fully, but there we go. So that is Pulse Width Modulation, the 8-bit computer way. And let me take you upstairs and we'll bring up the design for that Pulse Width Modulation controller and we'll let you see how that works. Alright, here's the schematic. This is just the schematic of the Pulse Width Modulation controller. The other I/O ports on that card are not shown. Okay, so here are the signals we require from the CPU here. We need the data bus, we need the read-write signal, a reset signal, and then we need the system clock. So the system clock comes in here to this prescaler. It's just a 74LS93 binary counter. And we can, divide by 1, divide by 2, divide by 4, divide by 8, and divide by 16. We had ours set up at divide by 8. For that example that I showed you on the scope. And what it does, comes in here, let's look at these chips now. These are the most important ones. We've got a 74 AC 574, and it's a latch. So it latches the data bus when the right signal is given. So when I write to that location, which was 33,024, it gets a right pulse and it latches what's on the data bus. So that's when we poke a value to it, it gets that value. Now that value is then presented on this side of the latch, and it gets presented to this chip here, the 74LS682, which is an 8-bit comparator. So it compares two numbers, this number here, this 8 bits here, to 8 bits over here. This 8 bits over here is from this 74HC590 8-bit counter. So the pulse clock comes in, this counter just keeps counting up. It counts from 0 to 255 and back to 0 again. It just keeps going around and around and around. And the comparator then compares this to this. So if I put a 128 into this, okay, that means Q1, Q2, Q3, Q4, Q5, Q6, Q0 will all be high. And this will count up until it gets one more than that. At that point, P, which comes from here, will be bigger than Q, which comes from here, and that'll drive this pin here, the output, it'll drive that high. And then for the next 127 cycles, it'll remain high. And of course, once it goes back to 0, that P will be less than Q, so this will go back to 0 again. So you're literally counting along like this until P gets to be greater than Q, and then back, bang, up it goes, and then when this resets back to 0, goes back down again. So no matter what number we put in here, we put in a tiny little number like 8, so just Q2 will be high, and this will only have to count up to 8 until Q3 or Q2 on it goes high. I should have labeled these P, shouldn't I? Anyway, until this pin goes high, and when this pin goes high and this pin goes high, then P is greater than Q and the output will go high, and it'll remain there for the next 248 counts. So that would be a very, very large pulse width with a very, very narrow off pulse width, and vice versa. If you had this, if you put out here 250 into here, then there'd be only 5 pulses where this will be high. So you have a very, very short pulse width. Now we were looking at a I divide by 8. So we had 14 megahertz coming in, which is the system clock. The system clock came in here, was divided by 8. So if let's do that math. So we got 14 million, and we divide that by 8. We get that, and then it takes full 256 cycles to cycle through this counter here. So we divide that then by 256. That gives us 6,835 hertz, or 6.836 kilohertz. And if we look over here, we can see that's the default we had. 6.83586 blah 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 hertz. So it's exactly right. It's what we calculated right here. Okay, that's it. That's how it works. And I use all these old chips. It's kind of like a part of my retro computing hobby. I build new retro computers and I run them with retro language like BASIC. The BASIC I use is called Enhanced BASIC. And it was created by a guy by the name of Lee Davidson, who's since passed away. It was created from Microsoft BASIC. So he took the Microsoft BASIC, disassembled it, and then added a few extra features into some of the commands and added a few extra commands, but still that old Microsoft BASIC with a few little bells and whistles added to it. It's pretty decent BASIC, actually. And so I build these out of these old parts, these 8-bit latches, 8-bit comparators, 8-bit counters, 4-bit counters, and so forth. And I have a lot of fun doing it. And to me, it's very interesting stuff to be able to create computers basically with older parts that never were created and are, in some ways considerably better than the computers that were created back in the day. Like this, for instance. Now, it does use a modern 6502, that little Vixen computer that I had there. Let me bring up a picture of that. Okay, so there's a picture of the one that we actually used. And if you look around in here, I have, this is an older one, probably running at a much lower frequency. And I have several of them built up that run at different frequencies. And, the way it's designed, I designed this so it could be put in a breadboard or it could be mounted into another system to control it, or it could be stacked. So you can have different interfaces on these boards and you can stack it up. However you want to build your system, that's the way you build it. Or you can do it like we did it today by putting it into that bus board and putting in cards into the bus. Well, anyway, that's it, folks. I hope we got something out of this. And if you want me to do more with this 8-bit computer hobby of mine, if you want me to present more of that, I will. There's definitely a lot of electronics in it. Some of it might take a lot more explaining. Taking you through the design of this little computer here might take several different episodes, but just let me know if you want me to do more of that. I'd be more than happy to, because right now I kind of do it off camera because I'm mostly concentrating on electronics. I don't know if you guys are interested at all in the computing side of things, especially from a development of computers, which really is digital electronics. Anyway, guys, that's all I have for you today. We'll see you in the next video. Thanks very much for joining me. Bye-bye.